Thanks a lot. And so yes, I keep writing on these lecture notes continuously, and I actually also correct them backwards. So even the things I've been true, because the organizers here are rather tough and asked me to have it ready at 10 a.m., no, 10 p.m. But so whatever you see here is whatever I've ready at 9:59 p.m. Yes. And then I'll correct it. But let's see. So I think yesterday I got to this mean field Thomas Fermi model, and this is what I would like to discuss a little bit more. So I had discussed the Thomas Fermi theory. Okay, maybe I should just mention again briefly this neutral TF atom. Start from there. So we had this Thomas Fermi equation for the neutral Thomas Fermi atom. So the actual Thomas Fermi equation was a little bit more complicated. It had this funny minus mu chemical potential positive part. But if you're doing the neutral Thomas Fermi atom, then the mu is actually 0, and the phi is greater than or equal to 0. So the equation looks much nicer, and it turned into this a nice nonlinear elliptic equation, at least away from the origin. And I had the discussion that if you look at an equation like that, so Laplacian phi to the 3/2, so it's understood here that phi is a non-negative function. If you look at the possible singularity at 0, there were two types. There were the weak singularity, where it behaves like 1 over x. And then there are this, one can see that the 1 over x essentially satisfies the equation because this thing will be 0. 1 over x is a harmonic function. So this is 0, and that is 1 over x to the 3/2, so much smaller than the 1. So for leading order, it still satisfies this equation. But what is didn't the light turn dimmer? But there are also the strong singularities that go like x to the -4, and we checked that we can get an exact solution to this of that form. And in fact, this is the limiting behavior of all the solutions as you go to infinity. It's also the limit pointwise. So you see the x to the -4 behavior as the limit for large x, and you also see it as the limit as z goes to infinity for each x. And we also notice that this infinite solution does satisfy the correct scaling. It's a fixed point for that scaling. And much of the universal behavior of atoms, the explanation that all atoms have more or less the same radius, is related to the fact that there is a fixed point for the scaling, and that there is a solution that's universal. The number b here that you can work out by just plugging in and calculating from the a, the fact that this b is a universal number relates to the fact that you have a universal behavior of larger. Okay, but then I started discussing this mean field Thomas Fermi model. And the point was that since we have a limit for Thomas Fermi theory, right, as z goes to infinity, the density, which is just the phi to the 3/2, remember the phi was would converge to x to the -4. So phi to the 3/2 will converge to x to the -6, again with some universal constant right there. So in the limit in Thomas Fermi theory, you do not see any shell structure or any periodicity. Thomas Fermi. So that's what I'm trying to say. We do not see any emerging periodicity. Thomas Fermi does not seem to describe that. But then, as I explained, we want to do the same as what chemists do when they do density functional theories. Robert did not discuss that aspect of density functional theories. This is what chemists call the Kohn-Sham theory, where they look at the density you get, they calculate the mean field from that, and then they put in orbitals. So that's what I do here. The mean field Thomas Fermi operator is the one where I take the mean field potential from Thomas Fermi theory and think of an independent Hamiltonian with this mean field. And now I want to fill in electrons, independent electrons. All the electrons feel sort of the mean field from all the rest, but other than that, they're actually now independent electrons, so it's much easier to study this. I mean, chemists never define really what is meant by Cohen-Sham, but in my understanding, this Thomas Fermi theory is the most primitive density functional theory, and this would be the most primitive Cohen-Sham theory. Maybe Mature understands these things better, but I think it's fair to present it in this way. So let's actually study this mean field model in greater detail. So first I wanted to argue, and I started that last time, that it is a very, very good approximation. It is, in fact, in some sense, and I will try to get to that, although I will not prove all the details, but it's actually as good as Hartree-Fock and reduced Hartree-Fock. Okay, that's an overstatement. It's from what we know, that our knowledge, it is as good. So we do not have a proof that Hartree-Fock, reduced Hartree-Fock is better than this model in approximation. I mean, I'm sure they are, and I'm sure we'll be able to prove it one day, but at this point, our state of our understanding, it's not. So actually, what I did prove already, I mean, we had this proof where we could choose any row tilde, if you remember, and I could estimate the interaction. We actually, oops, sorry. We could, we actually could prove a lower bound on the Hamiltonian in terms of the non-interacting Hamiltonian. We did it first with reduced Hartree-Fock, and the reason we did it first with reduced Hartree-Fock was that in that case, we had a very easy upper bound. Reduced Hartree-Fock was simply an upper bound in energy. But now I'm saying exactly the same proof where I just choose this slightly arbitrary density to be the Thomas Fermi density, I would get this lower bound. So this I actually proved. Now, well, I mean, I proved it using the Lipterian inequality, but now you've seen a proof also of the Lipterian. So that's very nice. And I should say, I will come to the Lieb-Oxford type bound, what Robert discussed earlier in this mean field approximation. Now, I did it to order z to the 7/4. I was very happy that I could do it better than z squared. But actually, and I would like to discuss this at some point, one can get down here to better than z to the 5/4. The statement here can be proved with a constant z 5/3. I mean, you might think, why do I worry about these small differences? Well, that's because you get more and more accurate and you reveal more and more the next term. The next term here is actually of order z 5/3. And we actually know it. So, and it's still this operator. I mean, the next terms are really just some constants. Right? So I would be able to prove this lower bound as an operator with this mean field. Well, this is just a constant. It's actually complicated constant, depends on Thomas Fermi theory, but it's just a constant. So I have a constant, and here I would have another constant that I could calculate so that this statement is actually true as a lower bound on operator. But I will only discuss it. I will not give all details of that, of proving that, because that's really complicated. Another thing that I will not do is the upper bound. See, in reduced Hartree-Fock, it was easy because it was simply a strict upper bound. Here, for the mean field Thomas Fermi theory, this is not as easy and is beyond the scope of what I was doing. Not that that is really difficult, and I will also try to explain it a little bit, but if you want to go all the way to 7/4 or 5/3, you actually, I mean, upper bounds are usually easier, but maybe difficult calculations. Right? You have to guess what a good trial wave function is, and then calculate. Right? And that's a bit complicated, but it's sort of clear what you want to do. You want to do an approximation to the ground state of this function there, which is the sum, the projection onto the negative eigenvalue. So you want to choose as a Hartree-Fock trial state, right? Or for this operator, you want to choose the sum of the negative eigenvalues. I mean, the projection onto the sum of the negative eigenvalues of this, and then do a calculation. And this can actually be done, and it can be done not only up to Z5 thirds, it can actually be done up to little over Z5 thirds. We can reveal the next term here, but that's really complicated. Okay, but what I wanted to discuss was, first of all, that how do we actually understand this operator and the sum of the negative eigenvalues? Right? Because the ground state of this operator is well approximated by the sum of the negative eigenvalues. Let me just point out a little difference here. And that is that I'm saying that I have Z electrons. That's because I was thinking of the neutral atom. I mentioned it already yesterday. The number of negative eigenvalues of this operator may not be equal to Z. We will see that it's almost equal to Z. The semi-classical approximation would be that it's Z, but it's not exactly Z. It could be less or it could be more. I've actually tried to convince students, bachelor students, to calculate it for me, the number of negative eigenvalues, to find out what it is. So I had a student who did it not for Thomas Fermi theory, but for some slightly easier. And actually, the semi-classical estimate for the number of negative eigenvalues, which would be Z, is amazingly good. I mean, she calculated for Z being 13,000, and I think it differed by 5. But this was not exactly for this model, but for some slightly easier model that was slightly easier to calculate. This was a bachelor student or bachelor project. But let me explain how semi-classics comes into this. So this is the operator I would like to analyze. This is the mean field Thomas Fermi Schrödinger operator. And notice that we have the scaling here, Z4 thirds, phi1 TF, Z1 third X. So now I do a rescaling. I replace X by Z to the -1 third X. But I discussed already last time, these things can be slightly confusing. What do we really mean when we do this, right? The idea that I have in mind is that you put in Z -1 third X here, so that says X. And then the Laplacian, if you change X to Z to the -1 third X, that's because it's two derivatives, it's in the denominator, so you get it Z to the 2/3 as a numerator. So here you would get a Z 2/3, and here you have a Z 4/3. And then what you can do, so I did it here the way it should be done correctly. You define a unitary operator. This is a unitary operator on L2 of R3. And you simply change the operator by that unitary. That's what I mean when I say rescale. And what you get is that you get a Z 2/3 in front of the Laplacian, as I described. The X there disappears because I described it heuristically. Then you have a Z 4/3 there. I pull out the Z 4/3, and then I have a Z -2/3 in front of the Laplacian. Now, the Z 4/3 in front, well, that's just a constant. Right? Whatever I calculate for this operator, if I want to know it for that one, I just multiply by Z. So I will forget for a while the Z 4/3, but we always have to remember to put it back in when we want to have the right energy. And then you see you have a small, when Z is large, you have a small parameter in front of the Laplacian. So it's semi-classic. So I call this parameter H, or I call Z to the -1 third H, and then this operator, which is written right there, looks very semi-classic. And now I can open up my books in all the heavy machinery of semi-classics. I don't know how well you know it. I'm not going to go through all that today, but I will tell you the results that you're doing. So I will analyze this operator now for a while from a semi-classical point of view when you let H go to 0. we have to remember that if we want to go back to what we really wanted to study, we have to set, we have to set h equal to z to the minus 1/3. We have to multiply by z 4/3. And we have to remember that the x is really z to the 1/3 of the x that I have in the middle. Okay, so let's do it step by step. So the simplest semi-classics you can do when you want to do the sum of the negative eigenvalues is what's called the Weil law. So the Weil law was originally for counting the number of eigenvalues of the Laplacian on a manifold or on a domain with Dirichlet boundary condition up to some level. Now, here we want to do it slightly differently. We have a Schrödinger operator with a semi-classical parameter, and we want to sum the negative eigenvalues. So not count them, but sum them. That's actually a little easier than it is to count. I discussed the counting before, and we could also have discussed the counting. The counting here is the thing that should be very close to 1, right? Because of it should be very close to rather the semi-classical value, which has an h to the minus 3. So it would be something like 2 times 2 pi h to the minus 3 times 1, because the semi-classical value for the Thomas family for z equal to 1 is a 1 electron. Now, when you do the number, a number is an integer. So as you vary the h, this integer will jump up and down. I mean, sometimes a new eigenvalue will come in. Right? I mean, as you make h smaller, the Laplacian becomes smaller, the whole operator becomes smaller. So that means that new eigenvalues can come in through 0. Whenever a new eigenvalue passes in through 0, I mean, I say pass, it's not an eigenvalue before. It's born at 0 and it becomes a negative eigenvalue. Whenever that happens, then the number will jump by 1. So there's no way you can sort of give a nice integral approximation of the number without making an error of at least of order 1, right? Because it jumps by. However, when you do the sum instead, then you're summing the negative eigenvalues. So when an eigenvalue is born, it's very small. I mean, we all are when we are born, right? And therefore, it hardly changes it. It doesn't jump by 1. So it's much easier, or you get much better estimates for the sum than you do for the. Okay, so what does Weil law say? Well, it says that the sum of the negative eigenvalue is what you get by doing a phase space integral. The phase space integral is 2 pi h to the minus 3. Then the classical symbol, where you replace the Laplacian by Laplacian by p squared, so you get 1/2 p squared. And you are integrating the same function as you have before, the negative part of the symbol. If you're integrating, the 2 there is because I'm still counting spin. So if you think it doesn't look like the usual way you're writing down Weil's formula, if you've seen it, then the extra 2 is just because I'm counting spin. So this is then the leading term. So the error for an object like this will be 2 pi h. I mean, the leading term is of order h minus 3, and the error is better as h goes to 0. It's a little over. This is a result that's nowadays fairly easy to prove. There are lots of different proofs of it. Some are pedestrian, some are extremely fancy, but all in all, it's fairly easy to prove Weil's law. I will not do it here. What you can do, however, and that's just pointing this out, there is that this integral, of course, you can do the p integration, and then you end up with this integral, right? There, which depends only on the Thomas family. So it's the phi Thomas family to the power 5. If you remember that the density was the phi, so the density was actually rho to the 2/3. This was the Thomas Fermi equation that the potential here was equal to rho to the 2/3. So if you plug in rho to the 2/3 there, you find rho to the 5/3, which was exactly what we had in the Newtonian. Right? So these types of semi-classical estimates relate to the Newtonian. And actually, if you get exactly this constant, this is what corresponds to the best constant. Expected to be the best constant in the Newtonian inequality, but we don't know. Okay, but I want to go further. I'm not happy with h minus 3, and particularly not with little o of h minus 3. I would like to expand this further. And now it gets complicated. See, the Weil law is true for any potential you might have here. Any potential you put in there would, let's say, positive potential, as long as this integral is finite. Now, maybe we should convince ourselves that this integral is finite. Remember that the Thomas Fermi potential goes like 1 over x at the origin. So at the origin, it's x to the minus 5/2, which is 5/2 is less than 3. So therefore, it's integrable at 0. At infinity, remember I told you it was x to the minus 4. So then this becomes x to the minus 10. That's variable. Right? So this is certainly integrable for Thomas Fermi. What I'm saying is any potential you would put in there, as long as the integral is 5 to the 5/2 is finite, then this formula is correct. Weil's law is an incredibly stable thing, and actually the way you prove it is by using a Leib-Turing inequality. That's how you can show that you don't need anything else than just this integral. But if I want to go further, then I need more. I need more knowledge on the phi to do a better approximation. And actually, if phi is very smooth and well behaved, you can usually do better and gain 2 powers of each. But this phi, the Coulomb potential, is not very nice. It has a Coulomb singularity. And the Coulomb singularity causes the next term. So the next term is what's called the Scott correction. And you cannot really write that as a nice integral. Actually, I'm not 100% sure that's true, but it's never been done. I think that there might actually be ways of doing it, but it has never been done. So I do have ideas for how one might actually be able to reveal this as an integral, but this has never been. Now, so where does it come from? How could one understand it? Well, one could actually understand it by plugging in hydrogen here instead. If I did 1 over x, just the pure hydrogen, pure 1 over x, then I know the eigenvalues explicitly. Now, for hydrogen, I would here get x to the minus 5/2 at infinity, but that's not integrable. So I cannot use hydrogen. Hydrogen would not work. Oh, but that's not such a big problem because I can just cut it off at some point. I'm really interested in understanding how 1 over x changes things. So I just take hydrogen and I don't care about what's happening at infinity. I take a big ball and I cut it off. And if I do and then you might say, oh, then you cannot do the calculations explicitly. True. So I could do something slightly differently. I could lift it up a little bit and only count the eigenvalues. Instead of counting all the negative eigenvalues, I could count all the ones below some slightly negative level. Then I'm fine. Then I can do it explicitly. This formula would be correct. I would add a little mu here that would subtract this little mu there. And then you might ask, what is the next correction? This is a calculation you can do explicitly. It's an exercise. Try to do it, and you get the 1/2 h to the minus. Now, proving that that's correct for any potential, not the pure hydrogen, that's a more complicated story. And actually was an open problem for a very long time. It was done by Scott, the way I just described it, which was not mathematically rigorous. But then it was first proved by Hughes, who was a student at Princeton, a PhD student at Princeton. This was his thesis, to prove that this 1/2 h minus 2 was a correct lower bound here. And then as an upper bound was then proved by Siegenshoff and Weikart. And I'll give you all the citation references a little bit later. Nowadays, we do not consider the 1/2 h minus 2 to be such a difficult thing to prove, although I think there might be an elegant proof out there that we haven't yet found, which would actually reveal it as a mean. So that explains, so I'm trying to reveal the different terms. So now I've revealed the h minus 2, I've gained one power of it. Now it gets complicated. I would like to go further in this semi-classical. I would like to gain another power. And this was actually achieved by Pfefferman and Secco. Although I should say that it was first done by Schwinger. Schwinger, who did quantum electrodynamics, when he, I don't know, at some point he got interested in atoms. And he was an amazing person at calculating. So he just sat down. I don't know what he did. Maybe he stood up and calculated. But he calculated it. It's an amazing achievement that he was able to do this. Pfefferman and Secco, I call it a monumental work. They wrote, well, we always say 1,000 pages, but I haven't counted it. But somewhere between 600 and 1,000 pages to get the next term, which Schwinger also found. And it's down here. And again, this term that I'm writing here would actually be the right term if you had a potential that was smooth and you would not have a Scott correction. But now you see that actually the Scott correction here is in such a way that the 1 over x there is actually killed by the Laplace. But if you think that the phi had a if you think of the delta function right there, I mean, you should do this integral. When you do calculate the Laplacian, you should do as I did before. You define this function outside of 0, not including 0, right? Because at 0, this Laplacian has a delta function, and then this thing would be x to the minus a half, which would be quite bad. So now. I mean, this is x to the minus a half, and the delta function would evaluate it at 0, which would be quite bad. But Pfefferman and Secco claim that you should think of this Laplacian phi defined away from 0, and the contribution from 0 is really singular because it's higher order than the 1 over h. It actually contributes to the h. Let me say a word about how they achieve this contribution, although I will not do it in detail, and in fact, I don't understand all the details. I've maybe read 50 of the 600 pages, but I have a feeling for what they do, but I have not done it. And some of it is computer assisted, because I will also get to that. At some point, they really need to understand something about a certain function being strictly concave. And I will try to maybe explain what the difficulty is here, and this is a known difficulty in semi-classical analysis. But what they do is that they do a WKB analysis. And if you do standard WKB, then you can approximate the eigenvalues. There's the Bohr-Sommerfeld relation in WKB that gives you a condition for the eigenvalues. But it sort of only gives sort of a leading order contribution. And they had to actually improve WKB to an order that had not been done before. So they do a very, very detailed WKB analysis, and then they sum up the eigenvalues. When you do a WKB analysis, that's because you're doing a one-dimensional problem. So this is a spherically symmetric potential, so you can do an angular momentum decomposition. You can do it for each angular momentum, this very detailed WKB analysis. And then you have to sum over the contribution from all the angular momentum. And you get an error for each angular momentum. And the problem is that these errors can sort of collaborate. And if they collaborate, then you're not going to, your error would be big O of h to the minus. And maybe I can just explain it on the board a little bit. You may know this. It turned out that when they summed over the angular momenta, it was a little bit, and trying to understand whether there was collaboration or no collaboration, they could change it into whether a certain function was strictly, well, in that case, it was concave. I guess it depends which way you're seeing it, right? I mean, there was still a thing that looked like that. And for that, there was a function, now I come to that function later on. This is a function that came from Thomas Fermi theory. Thomas Fermi theory is a solution to a non-trivial, non-linear elliptic equation. So actually, to strictly prove with bounds that this was strictly concave, they had to do a interval arithmetic and solve the equation very carefully. So that's how they eventually arrived and revealed the little orbits. Yeah. No. Okay. Okay. So no, that's not clear. That's not clear when you have the Coulomb symbol. But it. No. So they make statements like that, but that's probably in the page that I didn't read yet. But I can try to make the statement when phi is smooth. Because when phi is smooth, there is a term here that you would expect to get, right? Of this form. I mean, if it's a C0 infinity function, I think what you expect is exactly this expression. But it might not be revealed because you may have oscillations that are of order h to the -1. So what is it that determines whether you have those oscillations or not? That's understood. And that's related to when you look at the classical problem. It's related to a classical problem. If you look at the classical problem, and here we are summing the negative eigenvalues. So you want to understand what's happening at 0, or everything is when the energy is close to 0. So you look at the classical orbits on the 0 energy surface, right? Energy is a conserved quantity. So if you look at the classical problem, you look at the Hamiltonian flow, it will move on the energy 0 surface. If the set of if the set of closed classical orbits has 0 Liouville measure, I mean, the Liouville measure is invariant under the Hamiltonian flow. If it's 0, then you gain a little o of h to the 9. But you do not get any power. Of course, here I also didn't write the power. Pfefferman and Secco actually gain a little power because they do better than just saying that the set of closed orbits is 0. Actually, they claim that they actually prove that there are no closed orbits. And this is related to this strict concavity, but it's stronger than the strict concavity. For that, they actually use a complex analysis of the Thomas Fermi potential is real analytic away from the origin. And then using this, they can conclude that there are no closed orbits. But this term would be correct, but you would need smooth and having no closed orbits. The point with the harmonic oscillator is exactly that there are lots of closed orbits, right? Because it's an integral system. Okay. Yeah. Exactly. You should. Yes, I'll come to that right now. Yes. But you're exactly right. The way to understand this formula is to forget that phi has a singularity at the origin and calculate it only away from the origin, and that function you should then. But then, of course, this is something that's then only true for Thomas Fermi theory. But that formula is actually true for any potential. That understood as that you're integrating, not keeping the delta function at the origin. But I'll come to it right now. And I did not write it as rho 4/3, but it is rho 4/3, right? I say if you recall the Thomas Fermi equation, then the Laplacian phi is actually phi to the 3/2, right? If I just, Laplacian phi is a constant times phi to the 3/2, so this whole thing becomes phi squared. And so you actually get, and if you put in all the constants, you get this 2 divided by 9 pi cubed h phi squared. And I was thinking when preparing yesterday whether I should vote to the 4/3, but since I wanted to think semi-classically in terms of the potential, I decided to write phi squared everywhere. But of course, this was a wrong decision when I think about coming just after Robert's talk. So let me write it here. That phi squared in a moment. So now if I, as I said, I would plug back in the z to the minus 1/3, then remember we had to multiply by z 4/3. Right? There was this overall z 4/3 outside. And then h cubed is, h was z to the minus 1/3. Right? So this is something of order z. This is of order, I mean, this thing here is order z, and then you multiply by the z 4/3, so you get z 7/3. Here you get z 2/3, and you multiply by 4/3, that's 6/3, that's z squared. And the last term, you're gaining an h every time, you're gaining a 1/3 power, so you're getting to z 5/3. And the constant in front is this interval. And again, this is integrable. At the origin, it's x to the minus 2. And at infinity, it is x to the minus 3. So all of these two integrals are finite, and you're gaining the sum of these negative eigenvalues to little o. Now it's believed that the next term is an oscillator. I was talking about the oscillations you would see in the harmonic oscillator. You would see lots of oscillation for the infinite square. Well, there was no collaboration, but you still see oscillations, right? You just see them at a lower order. So, and here it is expected that there will be oscillations. Exactly to which order, I don't know. Right? Presumably, you're gaining a power of 1/3, but I think it's expected that the oscillations are large compared to z. So they're z 4/3, but still growing on that scale. But maybe smaller than any power that's bigger than 4/3. But I don't know. This has not. Pfefferman and Secco and Cordova, they have analyzed a term that contributes to this to some extent. But I don't know exactly what the conclusion was. But what I wanted to say, and this is now connecting to Robert's talk. Okay, now that we've gotten this far, right? So now I've understood the semi-classics to little o of z 5/3. Then why don't I go back? So the only thing I had proved, was that I had proved something to z 7/4. So why do I care about z 5/3? But let me now be ambitious and see, could I even go, what is missing here is understanding the exchange term. I ignored the exchange term. Now I'd like to understand. And I'm just claiming that that is the next term. I mean, I'm not giving you the details of the proof, but that part is actually not as difficult as analyzing this number. The difficult thing that Pfefferman and Stecco achieved in probably 700 out of the 750 pages was to analyze this one. Understanding the exchange term, they also did that. Is easy. So let me get to that one. Okay, but I'm just doing it just to give you an idea of how it's done. I'm not giving you all. So you want to write down the semi-classical projection onto the negative eigenvalue. And from a semi-classical perspective, that is looking at the phase space, 1/2 p squared phi 1 TF less than or equal to 0, and looking at the projection that's created from that classical. So I'm actually here writing down what's called the Weil quantization of the function on phase space, which is the characteristic function of when 1/2 p squared minus phi 1 from S Fermi is less than or equal. And that is this function right there. And so this is an integral kernel in the space and spin variables that approximates the projection onto the negative I. Now, if you look carefully about it, this actually does not satisfy that 0 is less than or equal to gamma less than or equal to 1. So I would not be allowed to use this thing as a trial state in reduced Hartree-Fock or Hartree-Fock. But I'm ignoring this at this point. Actually, there are ways that you can do other quantization. So instead of doing the Weil quantization, there's also the thing called Wick quantization. And Wick quantization preserves positivity. So if you instead here had used Wick quantization, then you would actually get something which is between 0 and 1, and then you can use it as a trial state. And that is actually how you made. It's the one. It is the one that is empty. You're right. Thank you. Thank you. Because with quantization, what? Weak. It's a very strong quantization, though. But anyway, let me just point out that. So let me try to do the calculations with the Weil quantization. And what? He's correcting my W again? Maybe you also insist that it's called Z and not Z. Okay, very good. You get the density by putting x equal to y up here and doing this. Right? If you put x equal to y, or not doing the, I mean doing the p integration. Right? If you put x equal to y, you have a 1, and then this thing is just integrating the fold. 1/2 p squared less than or equal to phi 1 CF of x. And if you do the calculation, you see you actually end up with the Thomas family. So that is has the correct Thomas family. But now let's plug it into the exchange term. But in doing that, the exchange term was not part of all this change of the z and the rescaling with semi-classics and so on. So I had to put back in the z to the 1/3 x up there when I do this. So I take this, and also here, I mean, if you wanted the Thomas Fermi, the correct Thomas Fermi density, right? The h cubed has a z, but you're missing the z to the 1/3. So I think I may be missing another thing. Yeah, I think so. I think here I'm actually missing another, and another, there should be another z. So that's the problem with doing the rescaling. It's always a bit complicated what you want to do. But recall that the scaling we did was, I have it. It was this thing here, right? So that you had the You replace the x with the z1/3 x, and then you multiply by z1/2. Right? And if you think of it in that way, think of this as being made up of eigenfunctions, right? It's an eigenfunction in x times eigenfunction in y. And then you have to do this transformation to both of them. So there should have been an extra z to the 1/2 there, which gives a z outside. Okay, but this is the expression for the, if I had remembered the right z, this is the expression for the exchange. And this is a calculation that we can actually do. Right? And I was thinking that I wanted to do that calculation because that is exactly where the, what was it, minus 1.44 or whatever is coming from in the, no, not from this one. 0.93. Yeah, sorry. Yeah. This is the thing that gives the Dirac constant in the row 4/3 correction, which is exactly the thing that you had in the Lieb-Oxford inequality. Of course, you're proving it with some other constant there. Right? But let me just start this calculation and maybe not finish it, but you can actually explicitly calculate it. I'm sure I will regret in a moment that I decided to do this calculation, but I hope you will all help me. So